Okay, now that we've gotten to know millimoles and moles just a little bit better, let's talk about molarity. This is the unit that's used most often in chemistry, so chemistry outside of healthcare, but you will see it in healthcare as well, and it is really an essential concentration unit to know. Molarity is the moles of the solute per liter of solution. So again, it's referring to the number of solute particles in 1 liter of solution. This is so important, it gets the shorthand capital M. If you see capital M all by itself in a chemistry measurement, so like, 5.0 capital M, that means there's that many moles of solute per 1 liter of solution. And so what if we want to look at the molarity of 0.9% sodium chloride solution? How can we convert this to a molarity unit? Because again, remember that this percentage, this mass volume percent, is a bit of a wonky unit where it's not that explicit on what it's containing. Maybe a little conversion with math could make it more useful. Remember that 1 mole of NaCl has a mass of 58.5 grams. This is the formula weight from the periodic table. And that 0.9% sodium chloride solution means that there's 0.9 grams for every 1 milliliter of solution, which means that there's 9 grams per 1,000 milliliters of solution. And we want to focus on the 1,000 milliliters or the 1 liter of solution, as that is the volume that is dealt with in molarity. So if we want to figure this out, well, we want to convert the 9 grams to moles. We know that 9 grams is the amount that's present per liter, and that happens to be 0.154 moles of sodium chloride. And because this is in 1 liter, we know that the molarity is going to be 0.154 moles per liter. We could convert this, right, to millimoles per liter if we wanted, and this here should say 154 millimoles per liter, or millimolarity. Looks like just a little bit of a typo at the end, but 154 millimolar is what we would call this. 0.154 molar, 154 millimolar. And, it may seem like making things more difficult to deal about particles, but it's really, really important because this is how the body deals with things. And furthermore, it doesn't just care about molecules. It also cares about particles. Water and its ability to be transported, remember osmosis from the beginning of this module, is based on the number of particles, not based on their mass. How many particles are there in the saltier solution? That's what really matters, not the molecules or the mass of the particles. And so because of this, and remember that when we have things like sodium chloride, they dissociate. 1 sodium chloride actually gives you 2 particles. And we may want to track that total number of particles. And for this, we track the osmolarity. This is the total number of dissolved particles per liter of solution, and it has units of osmoles per liter, which could be formed in something like this. And similar to the milli equivalence, what we really want to know is, well, what is our solute? How many particles is that solute turning into? And in the case of sodium chloride, 1 sodium chloride always turns into a sodium and a chloride. 1 sodium chloride becomes 2 different particles. And so if we want to track the osmolarity, we have to recognize that for every 1 mole of sodium chloride we have, we get 2 total osmoles. And so if we have this 0.154 molar sodium chloride, to convert that to the osmolarity, we simply multiply by 2. Right? For every 1 mole of sodium chloride, we get 2 osmoles, so we just multiply the molarity by 2, and this tells us that there are 0.308 osmoles per liter, or 308 milliosmoles per liter. And this is why normal saline is isotonic. Its osmolarity is pretty close to the concentration of blood in terms of osmolarity, which is around, for 290 milliosmoles per liter. Okay. Osmolarity is something that we want to be able to calculate as well. So let's try to bring it all together with this last practice question. Go ahead and pause here and see if you can work it out. One little hint, dextrose does not split up in solution. 1 dextrose becomes 1 dissolved particle. You'll use that at the very end, and it may look like you're not doing a lot of work, but it is a very significant step. So take some time, pause this one, and then I will go through my answers. All right, so what is the osmolarity of D5W 5% dextrose? Remember, this means 5 grams of dextrose per 100 grams of solution. And that is an important thing to remember that the percentage refers to. In 1 liter, right, we know that this is 5 grams per 100 milliliters, so it's about 50 grams per 1 liter. That's how much dextrose is present in 1 liter. And if we want to then know how much moles of dextrose this is, we need to do step 2, find the formula weight of dextrose, which we see is 6 carbon, 12 hydrogen, 6 oxygen, or 180 grams per mole, or milligrams per millimole. Next, we want to convert from grams to moles. We know that it's 50 grams of dextrose. We use this formula weight to convert. 1 mole goes with 180 grams, so we know it's 0.278 moles of dextrose. Next, we want to say, well, this is in a certain volume of water. We've smartly chosen the amount in 1 liter, so we know that this is 0.278 molar solution of dextrose. And finally, to convert from molarity to osmolarity, we want to multiply by the number of particles that the dextrose creates in solution. This one doesn't dissociate, 1 particle per dextrose, so 0.278 molar dextrose will also be 0.278 osmolar dextrose. This is a bit of a challenging problem. It wraps together a lot of the things we looked at in this video series, so if you did that, great work. If not, go ahead and keep practicing. Reach out to me if you have any questions, and I hope you've enjoyed learning a little bit more about how water interacts with biology.